Albert Einstein's theory of relativity is truly monumental. It completely reshaped how we see the entire cosmos. This isn't just some abstract scientific idea, it's fundamental. It provides a new language to describe reality itself. Relativity allows us to grasp the universe's workings, from the grandest scales of galaxies and galaxy clusters to the very nature of space and time we inhabit. Without Einstein's insights, modern physics as we know it simply wouldn't exist or make much sense. It stands as a majestic pillar of our scientific understanding, revealing the deep intertwined dance of space, time, and gravity. The genius behind this revolution was Albert Einstein. He was a profoundly curious individual, driven by deep questions. He dared to challenge even the revered laws of Isaac Newton. In the early years of the 20th century, his mind wandered. He pondered the mysteries of light's speed. He thought deeply about motion and how different observers perceive events. These profound contemplations sparked a scientific revolution. He didn't begin in a massive, well-funded laboratory. His primary tools were his incredible intellect and his bold, fearless imagination. His groundbreaking work didn't just adjust science, it utterly transformed it, showing us a new and astonishing reality. His first major breakthrough was special relativity, unveiled in 1905. This theory specifically addresses objects moving at constant speeds. Think of very, very high speeds, approaching the cosmic speed limit, the speed of light. Importantly, special relativity does not include the effects of gravity. Picture objects gliding through space in perfectly straight lines. Their velocity remains steady, never changing. It was special relativity that first revealed some truly shocking truths. It showed that space and time are not fixed, absolute quantities. Instead, they are dynamic. They are relative, depending entirely on the observer's own state of motion. This was a radical departure from classical physics, but Einstein knew his work was not yet complete after 1905. He continued his intellectual quest for another decade. He was determined to incorporate gravity into his framework. He also wanted to account for acceleration, which is any change in speed or direction. This relentless pursuit led to his masterpiece, General Relativity, presented in 1915. This theory is, in many ways, even more profound than special relativity. It offers an entirely new and beautiful description of gravity. No longer is gravity seen as a mysterious force pulling objects together. Instead, Einstein showed gravity as an intrinsic feature of space-time itself, a curvature caused by mass and energy. Special relativity is built upon two fundamental postulates or core ideas. These ideas might seem simple, but their consequences are extraordinary. First, the laws of physics are identical for all observers. This applies as long as you are moving at a constant velocity, not accelerating. It doesn't matter if you are standing still on Earth or if you are cruising in a spaceship at a steady speed. The physical rules that govern the universe remain the same. The second postulate is even more striking. The speed of light in a vacuum is constant. It is the same for all observers, regardless of their motion or the motion of the light source. It's the universe's ultimate speed limit. Nothing with mass can ever reach it. One of the most mind-bending consequences is time dilation. This means that time can pass at different rates for different observers. Imagine a special clock that uses beams of light bouncing between two mirrors. Now place this light clock on a very fast-moving spaceship. For an astronaut on that spaceship, the clock ticks normally. But for someone observing it from Earth, the situation is different. They would see the light in the spaceship's clock traveling a longer, diagonal path. Because the speed of light is constant, this longer path means the clock appears to tick slower. The faster the spaceship moves, the more pronounced this slowing of time becomes. Time itself is not absolute. Another strange effect predicted by special relativity is length contraction. Objects that are moving at extremely high velocities appear shorter. This shortening effect only occurs in the direction of their motion. Imagine a sleek, futuristic spaceship zooming past you at near light speed. To you, the stationary observer, it would look noticeably squished. It would appear shorter than it would if it were parked right next to you. However, for the pilot inside that incredibly fast spaceship, everything would appear completely normal. The ship's length, from their perspective, remains unchanged. Once again, what you observe depends entirely on your relative motion. This is another fascinating piece of Einstein's relativistic puzzle. Perhaps the most universally recognized outcome of special relativity is Einstein's iconic equation, E equals mc squared. In this equation, E represents energy, M stands for mass, and C is the speed of light, squared. This deceptively simple formula expresses a profound truth about the universe. It reveals that mass and energy are fundamentally interchangeable. They are two different forms of the same thing. Mass can be converted into an enormous amount of energy, and conversely, energy can be transformed into mass. This principle is the powerhouse behind the sun's radiant energy. It is also the fundamental concept that underpins nuclear power and nuclear weapons. A tiny amount of mass can unleash a truly staggering quantity of energy. Special relativity was a monumental achievement, a true game-changer for physics. However, it had a significant limitation. It did not include gravity. Its elegant principles only applied to scenarios involving constant speeds. It described objects moving in straight lines, devoid of any acceleration. Einstein was acutely aware that this picture was incomplete. The universe is filled with gravity. It's a force that shapes everything we see. It is also filled with objects that are constantly speeding up, slowing down, or changing direction. Therefore, Einstein knew he needed a more comprehensive theory, a general theory. He dedicated another 10 years of intense intellectual effort to this grand challenge. General relativity, his resulting masterpiece, offers a revolutionary new understanding of gravity. For centuries, Isaac Newton's view had dominated. Newton described gravity as a mysterious, invisible force, a kind of instantaneous pull exerted between any two objects possessing mass. Einstein, however, envisioned gravity in a radically different way. He proposed that mass and energy do not create a force in the traditional sense. Instead, they warp or curve the very fabric of space-time. Imagine space-time as a vast, flexible, four-dimensional trampoline. If you place a heavy bowling ball onto this trampoline, the fabric sags and curves around it. This sagging is analogous to how mass distorts space-time, creating what we perceive as gravity. So how do objects move in this curved space-time? Planets, for instance, do not orbit the sun because the sun is pulling on them with an invisible rope. Instead, they are simply following the curves, the indentations in space-time. These curves are created by the sun's immense mass. Think back to the bowling ball on the trampoline. If you roll a small marble nearby, it won't go in a straight line. It will curve inwards, perhaps even circling the bowling ball. This happens not because the bowling ball actively pulls the marble. It happens because the stretched fabric of the trampoline guides the marble's path. This is the essence of how gravity works according to Einstein. Objects follow the straightest possible paths through a curved space-time geometry. Such a radical departure from established physics required compelling evidence. Einstein's theory of general relativity made several testable predictions. One of the first major confirmations came from observations of starlight. During a total solar eclipse in 1919, astronomers measured the position of stars near the sun. They found that the light from these distant stars bent as it passed by the sun's gravitational field. The amount of bending was precisely what Einstein's theory had predicted. Another crucial piece of evidence was the peculiar orbit of the planet Mercury. Newton's laws of gravity couldn't perfectly account for subtle shifts in Mercury's elliptical path. General relativity, however, explained these anomalies with remarkable precision, solidifying its place as our best description of gravity. Believe it or not, you likely interact with Einstein's theories of relativity every single day. You might not even realize when it's happening. The Global Positioning System, or GPS, in your phone or car, relies heavily on them. This incredible technology uses a network of satellites orbiting the Earth. These satellites continuously transmit signals back to your device. Now, these satellites are moving very fast. According to special relativity, their internal clocks should therefore tick slightly slower than clocks on the ground. But there's another effect. They are also further away from Earth's gravitational pull. According to general relativity, this weaker gravity means their clocks should tick slightly faster. Both relativistic effects must be meticulously calculated and corrected for. Without these crucial adjustments, your GPS would quickly become inaccurate, off by several miles within just a day. General relativity also provided the theoretical framework that predicted the existence of black holes. These are some of the most extreme and fascinating objects in the cosmos. Black holes are regions of space-time where gravity is so incredibly intense that nothing can escape. Not even light, the fastest thing in the universe, can break free from their grip. Imagine a star far more massive than our own sun. When such a star exhausts its nuclear fuel, it can collapse catastrophically under its own immense gravity. It can shrink down to an infinitesimally small point of infinite density, known as a singularity. This process creates a black hole. We now have astonishing direct images of the shadows cast by black holes, spectacularly confirming Einstein's once theoretical predictions. They are cosmic monsters, yes, but also invaluable keys to understanding gravity in its most extreme forms. Furthermore, general relativity serves as the very bedrock of modern cosmology. It is the essential tool that allows us to understand the universe's origin, its evolution, and its ultimate fate. The prevailing Big Bang theory describes our universe as beginning in an incredibly hot, dense state. From this initial moment, it has been expanding and cooling for roughly 13.8 billion years. Einstein's field equations, the mathematical heart of general relativity, actually support this picture of cosmic expansion. In fact, they predicted it, although Einstein himself was initially skeptical of this particular implication of his own theory. Today, we have abundant observational evidence confirming this ongoing expansion. Relativity helps us piece together the grand narrative of our universe's history. The enduring legacy of Einstein's theories of relativity is simply immense. They have fundamentally transformed our perception of space, time, gravity, and the very fabric of the universe. They have not only deepened our understanding but also paved the way for numerous technological advancements. These theories continue to inspire new avenues of research and exploration daily. Scientists around the world are still delving into their profound implications. They are working on challenges like unifying relativity with quantum mechanics, or understanding mysterious phenomena like dark matter and dark energy. Relativity is far more than just a set of complex equations. It represents a revolutionary new way to perceive the cosmos, a shining testament to the power of human curiosity and intellectual endeavor. Its journey of discovery and impact is truly far from over.